This is the video for Chapter 4, Isomers, the Arrangement of Atoms in Space. Many students consider this the hardest chapter in organic chemistry. So we'll hopefully during this discussion make it not so hard. The first thing we're going to talk about is isomers, and we've talked about some already. Constitutional isomers, and we've also talked about cis-trans isomers. Let's review a few of these. So if I look at isomers, the definition is that they are molecules that have the same molecular formula, but they differ in the arrangement of their atoms. And there's two big types. Constitutional isomers, which are often called structural isomers, they differ in the connectivity of atoms. So they have the same molecular formula, but they have a different bonding pattern to the carbons. For example, if I look at C6H14, I can arrange those atoms, those carbon atoms, in many different ways. Here I have 1, 2, 3, 4, 5, 6 carbon atoms, and there's a branching here. Here I've arranged those 6 in a different way, my linear form, my T-butyl form, and my iso form here. You can see there are 5 different ways I can arrange those atoms, 6 carbons and 14 hydrogens, and they're all connected differently. Okay. That would be constitutional or structural isomers. There are also stereoisomers which have the same connectivity, meaning all the atoms are connected to the same other atoms, but they differ in the arrangement of those atoms in space. If I look at these two examples down here, you can see that I've drawn it with the carbon, and fluorine all in the plane of the board, the hydrogen coming out toward us, and the hydroxy group going into the board. There is a stereoisomer of that molecule where I still have 3 of these carbons in the plane, the carbon, and the fluorine. In this case, I have the hydroxy group coming out of the board and the hydrogen going into the board. These are considered stereoisomers of each other. They have some different chemical properties, they have some different physical properties, they are different molecules. Let's take a look at some constitutional isomers. I can have constitutional isomers that are not only connectivity but also functional group isomers. Here I have 2 carbons, 6 hydrogens, and 1 oxygen. It could be ethanol, or it could be dimethyl ether. Those two are considered constitutional isomers of each other. The atoms are connected together different. Also, the same thing's true with alkyl halides. I have 1 chlorobutane, where this chlorine is attached to the first carbon out there, or I could have 2 chlorobutane, where the chlorine is attached to the second carbon. Those are constitutional isomers of each other. Pentanes and isopentanes, one's linear, one's branched, same number of carbons, same number of hydrogens. And I can also look at different functional groups too. So here I have acetone with 3 carbons, 6 hydrogens, and 1 oxygen. Here I have propionaldehyde, 3 carbons, 6 hydrogens, and 1 oxygen, constitutional isomers of each other. The atoms are connected differently. When we're looking at stereoisomers, we have to look at them in 3 dimensions. They have the same connectivity, it's just their orientation in space that is different. So stereoisomers sometimes contain remarkably different physical, chemical, and biological properties, especially biological properties. After all, we do organic chemistry because we're looking at how it affects life, how it affects our lives and the lives around us and the plants and animals around us. This molecule here is fumaric acid. It has a melting point of 287 degrees. This is the trans isomer of this molecule. The cis isomer, same connectivity, same order of all the atoms, yet at the central double bond here, this is arranged in the cis configuration. This is often called maleic acid. It has a melting point of 138 degrees. So they have different physical properties. From a biological standpoint and a chemical standpoint, fumaric acid is a common food additive. It is included in many foods to keep them stable and add a little tartness to the flavor, like in peaches. They have fumaric acid if you look at the product label. Maleic acid, again, just the cis isomer of fumaric acid, it is poisonous, and it's used as an adhesion promoter for coating nails with zinc. So completely different properties, both biologically, chemically, and physically. Another famous stereoisomer is thalidomide. Okay, if I look at this isomer, if I look right at this carbon right here that has the asterisk next to it, it has a wedge showing this nitrogen part of the molecules coming out of the board. This is an antiemetic. It is a drug that was used in the 1950s, and it was used effectively against vomiting and nausea for pregnant women, and it was sold over the counter. Its stereoisomer, where that nitrogen-containing part of my molecule is going into the board, it is actually a teratogenic, a drug or substance capable of interfering with the development of fetuses and causing birth defects. So here we are using one stereoisomer to prevent nausea, morning sickness for pregnant women, and the other stereoisomer actually causing birth defects. It turns out when you manufacture the R-thalidomide, you make some of the S-thalidomide. Okay, so you can't separate them very easily, and so we were literally causing birth defects because of the stereochemistry. This asterisk here just identifies what we call an asymmetric carbon, which we're going to talk more about here soon, but that's where the difference is. The nitrogen coming out of the board, the nitrogen going into the board. Very, very important part of stereochemistry is its interaction with biological life. Let's now just talk first about the cis-trans stereochemistry on alkenes. So if we look at cis-trans isomers, they could either arise due to restrictions of being in a cyclic molecule. For example, here I have the CH3 and the hydroxy group in this molecule, cis-4-methylcyclohexanol. They're on the same side of the ring. I could also have them on opposite sides, so this would be trans-4-methylcyclohexanol. Another example here is in this cyclobutane molecule with a chlorine and bromine on it. If they're on the same side of the ring, in other words, they're both coming out of the page here, we call that the cis stereoisomer. If they're on opposite sides of the ring, we call that the trans stereoisomer. So substituents on the same side of the ring are cis, substituents on the opposite side of the ring are trans. The restriction created by a pi bond can also create stereoisomers. For example, if we look at this molecule here, I have a sigma bond between the two carbons, and I have a pi bond represented by these sort of purple p orbitals forming a second bond. I have the two methyl groups attached to those carbons going into the board, and I have the two hydrogens attached to the carbon going out of the board. If I could somehow break that pi bond, I could rotate about that double bond and form this new stereoisomer where I have the methyl group and one of the hydrogens going back into the board and one of the hydrogens and the methyl group coming out of the board. Those two are stereoisomers of each other. To break that double bond takes a lot of energy, and I have to go to extreme chemical conditions to actually do that. So typically we have stable cis and trans isomers. At this molecule down here, notice I have the two hydrogens on the same side of the double bond. We call that cis. Here I have the hydrogens on opposite sides of the double bond. We call that trans. You have to have that true to use the nomenclature cis and trans. I have to have a hydrogen on each of the carbons of the double bond in order to use the cis-trans nomenclature for these two different types of stereoisomers. Cis-trans isomers have very different physical properties. For example, if I look at this 2-butene, I can see that the cis isomer has a boiling point of 3.7 degrees, and the trans isomer has a boiling point of 0.9 degrees centigrade. They also have different dipole moments. Here I have my bond dipoles pointing in one direction toward the double bond here. In the trans isomer, they're both pointing in opposite equal directions, so I have a 0 dipole moment. If I look at the cis isomer of the 1,4-dimethylcyclohexane and the trans isomer of 1,4-dimethylcyclohexane, we can look at the physical properties also. A boiling point of 99.3 for the cis and a boiling point of 91.8 for the trans. That implies I can separate these two molecules from each other because they have different physical properties. I could just do a distillation and collect everything that comes over at 91.8 degrees relative to the higher boiling point. The same thing here. I can use boiling points to separate these two molecules. So in review, if the hydrogens are on the same side of the double bond, we call it cis, looking at these two blue ones here. So this molecule would be cis-2-pentene, or I could use the new nomenclature system, call it cis-pent-2-ene. Notice I put the word cis and a dash out in front of both of those names right there. Same methodology, whether I'm using the 1970s nomenclature system or the 1990s nomenclature system. If the hydrogens are on opposite sides of the double bond, we call that trans. Again, looking at the two hydrogens here shown in blue, I have trans-2-pentene or trans-pent-2-ene. Not all alkenes will show cis-trans isomerization. I have to have two hydrogens on each of the carbons. However, if I look at this molecule here that I'm highlighting here, I don't have a hydrogen on these two, both of these carbons right here. In fact, I have two methyl groups here, so there is no stereoisomer of this molecule. I have to have differences. I have two of the same thing here. If I look at this molecule, I have two hydrogens on that carbon. I cannot draw another molecule that would come up to be cis or trans. So if I exchange this hydrogen for this hydrogen, I'd have the same molecule. How about if I have a cycloalkene? The convention is that I have a double bond in a ring structure. It will be cis because it's much lower in energy. So cyclohexene, it's going to be the cis stereoisomer because I have a hydrogen coming off here and a hydrogen coming off here on the same side. Cyclooctene. If I get large enough, however, I can start to have both cis and trans. And if I do have a trans and a cis capabilities, I need to list them. So if I look at this double bond here, notice I could have a hydrogen coming out here and a hydrogen coming out here. They're both on the same side of the double bond, so that's cis cyclodecene. In this molecule, I have it arranged for they're in trans because I have a hydrogen coming off the top of this carbon. And I have hydrogen coming off the bottom of this carbon. They're in the trans configuration, so we would call this trans cyclodecene. I have to get up to approximately 10 carbons in order to have cis and trans stereoisomers of ring-based cycloalkenes. So, if I look at these two molecules, again, they cannot possibly be cis or trans isomers because my hydrogens, if I replaced one and moved one up here, I get the same molecule, and the same thing's true here. This molecule cannot be cis or trans, so I do not put that in the nomenclature system. I don't add the cis or trans out in front. If I look down here at this molecule, you can see I do have what is sort of set up to be cis or trans. If I exchange the hydrogen for the bromine and the bromine from the hydrogen, I get a different molecule. However, I can't use the cis-trans nomenclature because it fails there. I have to have a hydrogen on each of the carbons. So, therefore, to distinguish these two molecules from each other, which are stereoisomers of each other, I need another nomenclature system in order to do that. This new nomenclature system is based on what we call the EZ system. It's a nomenclature system patterned after the Cahn-Ingold-Prelog convention of assigning priority to atoms attached to the carbons of the double bond. There are other prioritizing systems out there. However, the Cahn-Ingold-Prelog system is still the most widely accepted for assigning priorities to the group. The priority is assigned according to atomic number, and that's atomic number of the atom directly bonded to the alkene carbon. This carbon, or this carbon, or in the second molecule, this carbon, or this carbon. Okay. So, if my atoms attached to my carbon are on the same side of the double bond, we call that a Z stereoisomer. If they're on opposite sides of the double bond, we call it an E stereoisomer. So let's do that. Let's assign priorities to this molecule. If I look at this molecule, I'm first going to assign priorities to the two atoms attached to the left carbon of my double bond. Bromine has a higher atomic number than chlorine, so priority 1, priority 2. If I look at the priorities on my second carbon across my double bond, carbon has a higher priority than hydrogen. Again, I'm looking at just the carbons attached to the double bond and the hydrogen attached to that double bond carbon. So this molecule, if the highest priority, which are 1 here, are on the same side, we call that the Z stereoisomer. If I look at this second molecule and we do the same thing, we assign priorities. Bromine is high priority over chlorine. And on this side of the molecule, my carbon is higher priority than hydrogen. Notice my highest priorities are now opposite sides of the molecule, so we call this the E stereoisomer. We can even do that with isotopes if we want to. If I have tritium, that's higher priority than deuterium, which is higher priority than hydrogen. So here's the EZ system. If my low priority are on the same side and the high priority on the same side, we call that the Z stereoisomer. And the Z stands for zusammen. It's a German word for meaning together on the same side. So if I look at this stereoisomer, if my highest priorities are on the opposite side and my lowest priorities are on opposite sides, we call it the E stereoisomer, which is Entgengen, which stands German for opposite sides of the double bond. So I can sort of go through my atom, through my double bond, and they're on opposite sides. I still set my priorities based on the carbons and the atoms that are attached to the carbon, atoms that are attached to that carbon. So when we name these systems, this molecule here, if I looked at it, I'd say I have 1, 2, 3 carbons. I have a double bond. So this is a 1 propene. This is a 1 chloro, 1 bromopropene. But if I assign priorities here, I can see that my priorities, I have my highest priority on the same side. So this is the Z stereoisomer. Z same side. If I have the other stereoisomer for 1 bromo, 1 chloropropene, where my highest priority atoms are on opposite sides, we call that the E stereoisomer. So if more than one alkene is present, we need to name each of them based on these EZ rules. So if I look at this molecule here, it's a 3-bromo octa-3,5-diene. I can see I've drawn it as if I have stereochemistry here. So I have a hydrogen sticking down here. That's usually the lowest priority ligand attached to a carbon. And I have a hydrogen sticking up here. So they're on opposite sides of each other. So the 5,6 alkene is going to be the opposite, so it's going to be the E stereoisomer. Notice I had to identify where on the molecule that started. So if I name this, I start off here at carbon 1, 2, 3, 4, 5. I get to my first alkene carbon, so this is 5E, 3-bromo-octa-3,5-diene. But in my second alkene here, starting at the number 3 carbon, bromine is high priority relative to this carbon. So this is 1, 2 priority. On this side of the alkene, I have a carbon and a hydrogen, so my carbon is highest priority. My bromine and my carbon are on the same side, so this is the Z stereoisomer. Again, identifying which carbon my double bond starts. So this is a 3Z, 5E-3-bromo-octa-3,5-diene. Let's now look at some more complex ligands attached to carbons that double bond. Assume there's a carbon down here that has a double bond attached to it, and all 4 of these. We're going to look at these 4 different ligands and assign priority to them. And we're going to do it based on atomic number. And so if we look at the atoms that are attached to the alkene directly, that first atom away from the carbon, I have a carbon, 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 and I have a hydrogen. So this is going to be my lowest priority ligand. So I can actually put a priority of 4 on that one right away because I know it's lowest. Now these 3 all have carbon, so I need to go out to the atoms that are attached to this. So I got to go 1 atom beyond that. And in this case, I have a hydrogen, hydrogen, a carbon attached to that carbon. So I have a CHH. Here I have a hydrogen, hydrogen, and a carbon attached to that carbon. Here I have a hydrogen, carbon, and a carbon. So this one is higher priority because I have a higher atomic number attached to that. So this would be highest priority. So here's my highest priority. Here's my lowest highest priority. And these 2 are now going to be 2 and 3. So now I need to move out 1 more atom from my second atom. I can't move out any further on the hydrogens. There's nothing attached to it. But if I move out from that atom, I get a bromine and 2 hydrogens. If I move out from this atom, I get 3 hydrogens. Therefore, this has higher priority of this. So this ligand over here on my left is going to be second highest priority, finally with third highest priority. Those are the Cahn-Ingold pre-log rules, moving out 1 atom at a time till I reach a different. Let's look at another example here, and we'll do the same thing. Okay. Assume that I have a alkene carbon right here, right here, right here, right here, and right here. So these are alkenes, and these are my ligands sticking off that carbon double bond. Let's go out to the first carbon. Oh, they all have carbon attached to my alkene carbon. So my first atoms are all the same. I can't rank them based on the Cahn-Ingold pre-log priority rules until I move out another atom. So let's move out 1 atom from there again. On this top example, I move out, I get a hydrogen, hydrogen, bromine. That's pretty high atomic number. Here I get a hydrogen and 2 chlorines. Okay. Here I get 3 carbons. Here I get 3 carbons. And here I get 2 hydrogens and a carbon. So if I look just at the second atom now, I can start to assign some priorities. Bromine has the highest atomic number, so we give that the highest priority. Chlorine has the second. And then I look down here at these ones. These are the same, I can't assign priority. These are the same, I can't assign priority. But these are lower priority than these 2, so I can assign priority here. That's my 5th highest of these 5 ligands. Now I got to look at the next carbon out from these carbons. So I go out 1 more time here. And in this molecule, I get 3 hydrogens, 3 hydrogens, 3 hydrogens. And in this molecule, I get 3 hydrogens, 3 hydrogens, 2 hydrogens, and a bromine. This is going to be my 3rd highest priority, followed by my 4th highest priority. Again, just working my way out 1 atom at a time. So if I look at this EZ nomenclature, I can look and do those same rules here. Here's my double bond. I'm going to assign priority to whatever's attached to this carbon. Let's say I have a carbon. I have a carbon. I need to move one further out. I got an oxygen, and I got an oxygen, so this is going to be higher priority. If I assign the priorities over on this atom, this is a carbon, this is a carbon, so I got to move one more out. Here I have 3 hydrogens. Here I have a hydrogen, 2 hydrogens, and a carbon. So this is going to be higher priority than the methyl group. This is an ethyl group. It's higher priority than methyl. So my highest priority on opposite sides of the double bond, I go down through there. They're on opposite sides. Opposite is the E isomer. If I do the same thing here, I recognize that I get the same priority system, but in this case, my highest priority ligands are on the same side, so same Z. What if I have double bonds and triple bonds in here? Okay, the Kahn-Ingold-Prelog system treats these double bonds and triple bonds by adding what we call ghost atoms to the atoms. And this is just used to assign priorities. It's not reality. It's just a methodology. So if I look at, say I had an alkene sticking off here, an alkene carbon here, an alkene carbon here, an alkene carbon here. So these are just ligands sticking off my alkene. What Kahn-Ingold-Prelog says is that I'm just going to take whatever this atom is on this double bond, and I'm going to add one to this one. And whatever this atom is, I'm going to add one to this one. So I'm sort of crisscrossing here. And I end up with just 2 generic carbons. No hydrogens, just 2 generic carbons. If I do the same thing with this carbon double bond nitrogen, I take this nitrogen, I move an extra nitrogen over here. I take this carbon and I move a nitrogen over here. And this becomes a carbon nitrogen and a nitrogen carbon. Again, this is just for naming. If I have a triple bond, for each one of my double bonds, I'm going to add 2 carbons here, and I'm going to add 2 carbons here. So my triple bond becomes this ligand. And if I have a carbonyl carbon, I'm going to add an oxygen to this carbon, and I'm going to add a carbon to this oxygen. Okay? So let's take a look at the priority system here. Again, assuming that if I start here with my alkene, I move one atom out, I get a carbon. I get a carbon on all 3 of these. So now I need to move out one more atom. That's one circled in blue here. And so I get a carbon-carbon-hydrogen, carbon-carbon-hydrogen. In this molecule, I get a nitrogen-nitrogen-hydrogen. And in this molecule, I get a carbon-carbon-carbon. And in this molecule, I get an oxygen-oxygen-oxygen. Okay. If I went to the 3rd atom out, I'd have a hydrogen-hydrogen-carbon. I'd have a hydrogen carbon only because there's only 2 things attached now as I move away from my alkene. Here I have a carbon-carbon-hydrogen, and finally I just have a carbon. And then I can prioritize these based on atomic number. So if I looked at those, oxygen has the highest atomic number, then nitrogen, then carbon. But here I have 2 carbons and a hydrogen. Here I have 3 carbons, so this would be my 3rd highest priority. This would be my 4th highest priority. And if I needed to, I might have to look at the 3rd atoms in some cases. So let's look at this molecule. I have an alkene here that looks like it should have stereochemistry because I can draw another stereoisomer. I've literally just switched 2 of these groups around, and I can't rotate about the central double bond. How about this double bond? Could I have cis or trans or E or Z here? No, because I got 2 hydrogens attached to one end of it. If I have 2 hydrogens attached to the carbon, I cannot have stereoisomerization at that alkene. So let's look how we assign priority to this molecule to determine why this is the Z stereoisomer and why this is the E stereoisomer. I'm going to do that on the next slide. So if we look here, let's first take a look at this side of the molecule. So I'm just going to assign priority to the first atom connected to this alkene carbon, and they're both carbons. So I need to move further out. I'm going to look at the second atom. In this case, I get 2 hydrogens and a carbon, recognizing that that carbon is bonded to that carbon. These hydrogens are just drawn in the way. And here I have a carbon with 2 hydrogens also. So there's still no difference, okay? Now I've reached a triple bond, so I need to start drawing my ghost atoms in. So when I do that, however, I go out one more atom here. You can see that I have a carbon, carbon, carbon. So here's a carbon, carbon, carbon. Up on the top here, I have 2 hydrogens and oxygen. Oh, oxygen has a higher atomic number than carbon, so that's going to be my highest priority. If I go to the right-hand side here, and I look at one atom out, I get carbons on both of those. They're the same. I got to go another atom out. And in this case, I hit a double bond on this top ligand here, so I got to draw my ghost atoms in now. And then as I move out from there, you can see I have a carbon and a hydrogen and a carbon. Hydrogen, carbon, carbon. If I look at this one, I have a carbon and a hydrogen, hydrogen. So this is higher priority than the one on the top. The one on top is higher priority than the one on the bottom. So that's how all this comes together to be the Z stereoisomer. So if I look at these molecules right here, I could do the same thing. In this case, I would assign priorities to the different groups moving out. You should do this for practice. You should take this slide, move out one atom from the alkene carbons, assign priorities, and then determine which side of the double bond the highest priority molecules are, and make sure you come up with the right stereoisomers. This is sort of a practice problem.